Okay, hey. So today we're going to talk about two topics. On the first, probably 30 minutes, we'll be talking about simulation. So more about simulations because it's nearly the end. So we're going to do advanced simulations, or technically complex. More complicated systems. And the second, so the last like 15 minutes or so, we're going to introduce Plannero, which is a startup focusing on scheduling, so using artificial intelligence for scheduling. So I'm going to firstly talk about simulations.
Daniel.
Yeah?
Remember, you've only got 40.
Yeah. So first, yeah. So remember from the first few lessons, we talked about Markov Chains. So remember what a Markov chain is? If I have some sort of person from position 0, and I have some sort of elevator, right, in the airport, the person can only move along the elevator, right? So if this is position 1, 2, 3, 4, 5, then the probability of going from state 0 to state 1 is 100%, right? Because if the elevator is working, the person has to move next. If the elevator is broken, well, that's a different story. But if the elevator is not broken, then the person continuously moves. So the probability of 1 to 2 is also 100%. Right, and so on. Until you go from this state, right, 5 to something, right, this state, I'm just going to call this as outside. The probability of going from 5 to outside is also 100%. But if you're already in the outside area, right, there's no more elevator, then the probability of outside going to somewhere else is obviously 0, right? There's nowhere else to go. This is the last state. So if you do a transition matrix, then the transition matrix would just be a big matrix, right? State 1, 2, 3, 4, 5, and outside. And then this is from 0 to 0, 0 to 1, 0 to 2, 3, 4, 5, and nothing. And if you just write all of this down, right, the probability of 0 to 1, right, 0 to 1 is 1, right, 100%. The probability of 1 to 2 is 100%, so 1 to 2. So it's a diagonal matrix shifted, right? So it looks something like this. Right, and nothing to nothing is 100%, right? The person stays in the nothing area. And everything else is zeros. Right, everything else is zeros. And this is a transition matrix. Right, so if you want to evolve the state, so if you have this simulation of the elevator, if you want to know the fifth state, then you just do t to the power of 5. Right, the powers mean the state. So that's just a revision of Markov chains. Now I'm going to talk about some applications, some real-world applications of what you can do with them. And I'm going to show you some examples. The first one that I'm going to talk about is traffic congestion. So for example, let's say that you have one city called A, another city called B. Okay, I'm just going to keep two states. And there is some sort of highway. Right? There's a highway between A and B. So we know that A has a population of 1 million, right? And B has a population of, let's say, 10 million, like a mega city. And during the peak hours, we know that A wants to go to B to work, right? Let's just say that every single peak hour, every single day, 20,000 people, no, let's say 200,000. That's not a very realistic number. Let's just 200,000 people go to B to work, right? And B, the people go to A as well to work, right? Let's just say there's 10,000, not very, let's say 100,000. So if you do proportions, right, 200,000 is approximately 20% of people from A go to B. And if it's 100,000, then I think it's 1%, is it? Yeah, 1% from B to A, right? So that's peak hour. So this is from like 6 a.m. to, let's just say, 12 p.m. And then let's say that people go back home, right? So go home. And go home is approximately the same number of people. Some people probably stay in B. So if you do this way, how many people from B go to A? Approximately 200,000, right? Because 2,000 people go to B, and then 200,000 people go back. And then this one, 100,000 people go back, right? From this, because the 100,000 people went to work, they're already in A, but when they want to go back home, then 100,000 people need to go back home. Okay, assuming that these are the numbers. Obviously this is wrong, so some people might like rent and stay in B, so maybe this number drops to 180,000. But let's just say it's 200,000 for now. So now we have one transition matrix, right? The probability of going from A to B is 20%, 0.2. The probability of B going to A, so that's going back home. Oh, sorry, that's the, so this is peak hour time, the morning time, right? In the morning time, 1% go to A, right? And the probability of staying home is 99%, right? Because it's 0.01 go outside, then that means 99% has to stay home. But because 20% go to B, and 80% stay home, right? So that's morning time. In the evening, so when people go home, right, the Markov chain is reversed. So the probability of B going to A is 200,000, right? But remember, originally we had 1 million people here, and we have 10 million people here. So after state 1, 200,000 people go here, so now B has 10 million, 200,000, right? That's currently B in the morning. But don't forget, B also goes to A, right? And that is 0.01%. And 0.01% of this number is 1 million. So you just minus 1 million. Oh, sorry, 100,000. So finally, this is how many people is in B, right? This is just using basic maths. We have that this many people is in B, in state 1. State 0, technically. When you go back home, what happens is that we need 200,000 people to go back home, right? So it's just ratios. 200,000 divided by 10, 100, 000. And this is your probability of going from B to A. Right, so you just write this number. I don't know what that is. Let's just assume it's approximately 20%. I don't know, 19% or something. Right, this is just calculating. And then remember, the probability of going from home from A to B, how do we do that? Well, remember, how many people is in A at the beginning? 1 million, right? However, we know that from B, 200,000 people go to A. So now the population is this. Right? So that's the population of A. But remember, people also go to B, right? So you have to minus 200,000. So the population of A is still 1 million. Right? Considering going in, B go to A, and A leaving B. So currently the population of A is 100,000. And remember, our aim is to find the probability of going from A to B. And we know that 200,000 people go back home, right? So that means the probability is 0.2. So this is your home matrix, going home. Right, and then the state, if you go staying in B, 0.81. And the state, and staying from A, right, staying in A is still 0.8. So now you have two transition matrices. Obviously these numbers will change, okay? So that's what I mean by complex random Markov chains. These probabilities will actually change. Okay, so in the morning time, I'm going to make this matrix M, right? And the M matrix is just the probability transition matrix, right? A to A is 80%, A to B is 20%, B to A is 0.01, and B to B, so staying home, is 0.99. You can see all the rows add to 1. That's just a Markov chain property. And this is the morning matrix, right? And this is the evening matrix when people go home. Right, how do people go home? A to A, they stay 80% at home. Right, these are the people like kids that don't go to work. Right, A to B is 20% also. And B to A is 0.19. And B to B, staying home, is 0.81. Right, as you can see, the top row is the same. But the bottom row is different, right? It's kind of reversed. Just a little note, every single day these probabilities will change. Because some people are sick, right? They don't want to go to work. There might be some sort of event. So pretend that there's like some sort of football event in A, right? Then more people go to A, right? More people go to A. So the transition matrix will change. But anyways, let's say that we have transition matrix, the morning and the evening, right? And remember, the population matrix, this is called the transition matrix. The population matrix is just how much population is in A and how much population is in B, right? And originally we had 1 million and 10 million. That's your population matrix. And if you use the population matrix, now you can just do matrix multiplication. The population matrix times M, I think that's correct. Oh no, sorry, it's the morning matrix times P, right, is, so if you have some sort of time period, Monday, Tuesday, and Wednesday, at 6 o'clock on Monday, this is how much population is at 6 o'clock, right? At 10 p.m., so in the nighttime, you have to times it again, right? So this is actually the evening matrix times, so at 6 a.m., it's morning times the population matrix. At 10 p.m., which is the nighttime, it's the evening matrix times the morning matrix times the population matrix. And Tuesday morning is the morning matrix times the evening matrix times the morning matrix times the population matrix, and so on. Right? As you can see, it alternates. So in every single evening and morning, the timing is different, right? So it's morning times the population matrix, and then the evening, right, going back home, and then this is going to work, right, and this is going back home, and this is going to work, and this is going back home. As you can see, it's a chain. So now what do I mean by more complicated systems? So let's say that you're a city official, right? So I'm going to keep these numbers. Actually, no need. So let's say that you're a city official, and let's say that you have A and B, right? The same cities. 1 million people and 10 million people. This is going to be an important application. So let's say, remember I told you there was a highway? So let's say there's a highway. There's a highway between A and B, okay? And approximately, there are 3 lanes which go this way, and there are 2 lanes which go this way, okay? So let's say that in 3 lanes, in every single 1 hour, the motorway can only take 10,000 cars. And there are only 2 lanes this way, and they can only take, let's just say 5,000. Okay? Actually, this will be, okay, 15,000 and 5,000, right? So this is your road network. So our problem is, we want to see what happens if we add 1 more lane to this way. Let's say that we add 1 more lane, then let's just say that it increases to 15,000, the same as this one. Let's see what actually happens to the traffic flow. That's actually the question. So originally we had 5,000, right? People can go from B to A. Actually, let's do easier numbers. 20,000 and 10,000, right? So this is the road capacity. So we want to see what happens if we add 1 extra lane. What happens to the congestion? That's the question. This is a very common question in road planning. So let's see what happens. So remember, every single 1 hour, 20,000 cars go from A to B, right? So A to B, there are 20,000 cars, right? Every single 1 hour. So if it's 2 hours, then the cars is 40,000, right? If it's 3 hours, then the capacity is 60,000, and so on. So if you do a transition matrix, you can clearly see that the probability of going from A to B is, right, so how do we do this? Remember I call this complex Markov chains, it's because the probabilities actually are changing. Right, so remember in state 1 there is 1 million people. Right, and we know that 200,000 people want to go to B. And there's only 1 road. Okay, let's just say there's only 1 road. There's obviously going to be multiple roads. But 200,000 people want to go from A to B at 6 a.m. But the road can only hold 20,000 people. So technically the real probability of going from A to B is only only 20,000. Right? Divided by 1 million. Which is 0.02. That's actually the probability because of this road constraint. right? Only 20,000 cars can go from A to B. So our probability is actually reduced. But remember, because of traffic jam, at 7 a.m., right, there's how many people? So remember, the road can only hold 20,000 people. That means that 180,000 people is still stuck on the road, right? They're still waiting for the cars to move. So in 180,000 people is now the new probability, right? So the new probability so this is hour 1. At hour 2, right? There is 180,000 people want to go from A to B, right? And the road can only hold 20,000 cars. However, remember now, there's actually less cars. So the probability is actually 20,000 divided by 180,000. And that is, what is that? I don't know, 2 divided by 18. It's a larger number than 0.02. Right? So the probability has actually increased. So as you can see in the 3rd hour, right, we minus that, so now A only has 160,000 cars. And the probability from A to B has actually been now is 16. Yeah, divided by 180. Sorry. 2 divided by 16. Yeah? The 4th hour is 2 divided by 14, and so on. Until 0.
Daniel,
Yeah?
quick question. Why is it for the first one the denominator is actually
Yeah?
when you first calculate 0.02,
Yes.
understand the denominator would be 1 million, is that correct?
Okay, so 1 million people actually, so in A, there's 1 million people. But only 200,000 people want to go to work from A to B, correct?
Yeah.
But the road can only support 20,000.
Yeah.
So it's actually 20,000. Oh, did I do it wrong? Oh, sorry, it's 20,000 divided by 200,000.
Do you want to address the people outside?
Huh? Oh, it's 0.1, I think. Huh? No, they can just wait, don't worry. Yeah.
Cool.
Okay, yeah, sorry, it's 0.1. Just say wait. Okay, I think I just did the math
Yeah,
wrong.
yeah. And also you mentioned that every hour there's 20,000 people want to go on. Is that correct?
Correct, because there's 200,000 in the waiting list,
Sure.
but the road can only hold 20,000. So every single 1 hour, the number reduces to 180,000, right?
So in the 2nd hour, would you not add another 20,000 to that? Because isn't there an additional 20,000 once you go from A to B? Or is that?
But the road can only hold 20,000. So the probability is still 20,000. Oh, the number of cars that can go.
Again, yeah.
But the denominator has decreased.
But if we're saying every hour there's actually 20 extra thousand once you go from A to B?
No, so in the morning, only 200,000 people want to go.
Okay, no.
That's the total number of people. But as you can see, every single hour, the road is congested. It can't transport that many cars.
Okay, so it's a number per day.
Yes, correct. Number per day. But you can change whatever number you like. I'm just giving an example of number per day. But you can see the probability keeps reducing. Right? The first probability is 20,000 divided by 200,000. The next hour is 20,000. So the numerator doesn't change, but the denominator changes to 180,000. Right? And then it's 20,000 divided by, and then it's this, right? It keeps going until your last hour. You can see there's some people which can't get on the road. So obviously you have to use other road systems, but let's just say there's one highway system. So now let's go back to the original question, which is what happens if I add a new lane. Oh, so I was going to say, so we already have the probabilities. So this is actually the road matrix, right? The road transportation matrix of time 1, right? R1, we just fill the transit matrix. This is R2, this is R3, this is R4, and so on. Right, and then you just do probability timesing. So the population matrix, you just get R1 times R2 times R3 times R4 and so on. That's your Markov chain representation. So the question is, after you times this, you actually have how much capacity of your road is actually used. So some sort of number. Your populations are A and B. There's some sort of number over here. So let's say they want to increase the road. Remember the old road can only hold 20,000. Let's say they want to add a new lane that now holds 30,000. So there's 10,000 new extra lane. Then remember, these road probabilities will change. Right? All of this will change. Now it's 30,000 divided by 200,000. And then you have to minus the 30,000. And so on. So the probability has actually changed. It has increased. And then to find how effective your road actually is, you just do this, the old one, minus the new one. And then you get your new capacity. So obviously this is quite stupid. If you only have one highway, you can just do it by hand. But let's say that we have A to B. There is multiple roads. Right? And sometimes you can go from A to C and then C to B. Right? And then you can go from A to D and then D to E and then E to B. Right? This is a very complicated real-world road system. And you can't do this by hand anymore, right? It's way too complicated. And to actually find out how many people from A go to B, we have census data. And that's where you get the data from. And the road capacities is estimated. So you can actually estimate the road capacity. If there's one lane, how many traffic lights? You work out the probability of from this place, skip the traffic light. What is the probability of a traffic light working? And then you can find the total road capacity. What's the time?
It is 40.
Okay.
Nearly.
Oh, you can.
Don't leave
Yeah,
it
you can.
outside too long.
Oh, you can tell them to come. Okay, so now I'm going to talk about scheduling, Plannero. So I'm actually. So I was gonna talk about data science applications, anyways, in the AI lectures. So I'm actually the current AI engineer for Plannero, but I'm just going to tell you what we do. So this is a real-life application of AI algorithms. So what Plannero does is, let's say that we have some sort of calendar, right? So some sort of, you have assignment 1, assignment 2, assignment 3, and test 1. Each of them has some sort of weighting, 20%, 10%, 30%, and your test is like 50%. Right? And we also have due dates. Your due date is 2 weeks, 3 weeks, 3 weeks, and 5 weeks. This is your information, right? And your course code, let's just say is comp 1511, 2521, 3311, and 9844, something like this. Right? All column. Let's just say, this is just an example. But anyways, our task is given this data, right? How do we actually optimize the calendar for the student? How do we actually optimize the schedule? When should you do assignment 1? When should you do assignment 2? When should you do assignment 3 and test 1? How do we actually arrange these tasks in such a way to efficiently manage your time? So old algorithms, they can easily do this if you have one column. Just the weighting. This is what all algorithms can do. It's called greedy algorithms. So what greedy algorithms does is, you just look at the highest weighting, so 50%, and you allocate time test 1 first. Right? So you should study test 1, test 1, test 1, test 1, and then look at the second highest rating, this one, right? Then you allocate assignment 3. So you have to do assignment 3, assignment 3, assignment 3, and so on. And then the next highest rating is assignment 1. And then assignment 1, assignment 1, assignment 1, and then assignment 2 is last. This is old algorithms. So the problem we have is, what happens if you have multiple columns? That's actually a problem. So this is an NP complete problem. Right? So non-polynomial time. So what NP complete means is that there is no feasible algorithm to effectively manage your time. There is no feasible algorithm. Right? An example of a non-feasible algorithm is, for example, a very common example is the knapsack problem. So the knapsack problem is when you have, so an example of a knapsack problem is, let's say that we have one block, right, like this. And we have multiple blocks. Let's say that another block is this, another block is this, and another block is this. Okay, we have different blocks of different height and different width, right? So our aim is to maximize the total number of height. Maximize the height, maximize the total height, right? So you can stack these together, right? You stack this one, then you put that one on, and then you put that one on, and then you put that one on. And you want to have the maximum height, right? But the constraint is, the top one has to be shorter width than the bottom one, right? You can't do this. It has to look like this. You cannot have this. This is not allowed. So as you can see, this one, you're not allowed to put on top of this. Right? So, but that's the problem. The problem is you have to stack them in such a way that you get the maximum height. So this is actually NP complete. There is no algorithm which allows you to do this feasibly. You have to do it, you have to check everything. Well, if there's only one dimension, it should be fine. But let's say that you can't rotate the blocks, right? You can't actually get this and rotate it. You can't do this. Right? That's going to complicate the problem. But as you can see, there are two different conditions you have to check. The width and the height. You have to do two different stuff, right? And the complexity is n squared. So what it means, you have to check everything. So that's the same as our problem. We have to check everything. So if you have your weighting, right, your deadline, you can have other columns like course difficulty, right, so you have your weighting like 20%, 30%, blah. Your deadline is like 2 weeks, 1 week, and so on. Your difficulty is like, I don't know, 5, 10, divided by 10, right? The total difficulty is 10. Your importance, for example, is 0.5, 1, 10, right? That's, the first one's not that important. Divided by 10, that's the maximum. But anyways, you can see you have multiple columns. As you increase the number of columns, the complexity increases, right? If you have one column, the complexity is approximately ON, approximately. I think it actually is ON. And if you have 2 columns, then it's ON squared. If you have 3 columns, I think that's when problems happen. It's actually, I don't think so. It's not n cubed. I think it's exponential time after you have 3 columns. I think. I'm not exactly sure. And then if you have 4 columns, it gets even worse. So it's more than. Okay, so as you can see, there's a problem. You can't actually effectively manage a calendar if you have so many different columns. So what Plannero does is we use artificial intelligence to do it for us. If you can't do this hard problem, let's just approximate. The best approximation possible. So, as you know, gradient descent is the algorithm that is used to optimize a cost function, right? So this is in all machine learning algorithms. In all machine learning algorithms, normally we use the mean squared error, which is the sum of your predictions minus the real value squared divided by n, right? That's the number of total stuff. Actually, it's divided by 2 for easy computation, because if you do the derivative, the 2 cancels out. But anyways, this is your mean squared error, right? This is what gradient descent and all machine learning algorithms use. Most of them use that. There's also mean absolute error. This is mean squared error. Mean absolute error is just the absolute value. So 1 divided by n, the sum of all the absolute values. This is the mean absolute error. You also have other types of errors like Huber loss. This is to stop outliers. I'm not going to write the formula, but actually there's lots. There's also the KL divergence. This is used in autoencoders. But anyways, there's lots of different cost functions. So what gradient descent does is that this is actually also an example of a non-polynomial time algorithm. You have to check everything. Well, actually, you can run in polynomial time. But anyways, so if you have some sort of cost, this is your cost function, and our aim is to find the lowest cost, right? This is the lowest cost. But you can't just find it like that, right? You have to start from here. This is your random starting point. And then you have to iterate, right? So obviously, in this one, if you start from here, this is not going to work. Right? Because if you start from here, you will just keep going down. Because gradient descent, right? You descend down the value, and then you stop here, and then you fail. But that's actually the global optima. This is the global minimum. But if you start from here, you fail. So what you have to do is you have to randomly, so every single time for your neural network or whatever machine learning algorithm, you randomly initialize like 10 times or something. This is your first random initialization and fail. Then you initialize again from here, and then you go down, fail. Well, it's getting closer. And then you randomly initialize again. Oh, there, you got a global minimum. That's what you do. There are some new algorithms called Cyclical. There is I think a new paper was just published like a few days ago. What they do is they call something called cyclical learning rate. And what cyclical learning rate is it tries to find the global optima without you doing anything. all you need to do is remember there is something called decaying learning rate. The learning rate starts at 0.01, and then you keep reducing the learning rate by some sort of factor until it's 0 and then you, well, some small factor and then you stop. Right? This is called decaying learning rate. The decaying alpha. What's the time?
You've got 12 minutes.
Okay, decaying learning rate, right? This is your learning rate decaying. This is what machine learning algorithms use. I don't think so Atom Optimizer actually uses decaying learning rate. They use adaptive learning rate. It's a bit different. Adaptive learning rate or adaptive alpha, what it does is the learning rate actually changes automatically. But in stochastic gradient descent, so vanilla stochastic gradient descent, we use decaying learning rate. So what decaying learning rate means is your step size gets smaller and smaller and smaller. So let's say that you have some sort of cost function. Your first step size is very large. But then we want to make the step size smaller. And then smaller, and then smaller, smaller, right? Until you converge. That's your learning rate, the decaying one. So what the new researchers found was that you can do cyclical learning rate. So what is cyclical learning rate? There are two different ways. The first one is called cosine cyclical learning rate. And what happens is you just approximate you just do cosine graph. Well, I think it's, but you shift it up. And what this does is that this is your learning rate. Your learning rate starts from 0.01, but it goes down to nearly 0. So it's like 0.001. And then it increases to 0.01. And then it decreases. And then it increases. And then it decreases. And then it increases. And every single time, over here, you save your model. Save it. Save it. And what happens when you save your model is that now you actually have three local minima. So if your cost function look like this, if you start from here, right, remember the learning rate big, but then it gets smaller, 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 smaller. Over here, it stops. You save the model. But then remember, the learning rate is suddenly increased to all the way to 0.01. And what it means is now you skipped, you went over here. Right? That's what it means. You surpass this area because the learning rate is so large, you do such a large step that you actually go outside of the valley. And then then you go from here. And then you go smaller, smaller, smaller. And then, oh, there, we have another local minimum. But then again, you increase your learning rate. And then you bypass this entire area. You go to here. And this will fail, right? Because you still go down, 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 and you're still here. But then the third iteration, you bypass the learning, you bypass this area again. And now you're here. And then this is your new saving point. Right? You save it here as well. And you keep doing it. And you keep until you actually find the global optimum. So after you do this like 10 times or something, you have 10 different models. Model 1, Model 2, Model 3, la 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 la. And you choose the best loss. Right? Because now we actually make the model find 10 different local optima. So anyways, what is the whole point of this? I was just telling you about it. So in old methods of, so in calendar, when you want to schedule your calendar, right, you want to optimize your time for efficiency, you want to do all the stuff necessary. What Plannero has done, the first step, is we use artificial intelligence algorithms. Right? We use optimization techniques, we develop some sort of back-end cost function, some sort of cost function. And this cost function is what we want to minimize. There is some sort of cost function at the back end. Right? And we incorporate stuff like Google. Okay, so we have a cost function that we want to optimize, and what it does is that we have multiple columns, like your weighting, your deadline, your other factors, and we optimize your calendar effectively using optimization methods. So one other piece of Plannero, which is exceptionally interesting, is that we actually extended what we can do with AI. So remember, AI is used for prediction, right? And optimization. These are the two main factors of AI. So I just showed you the optimization part. So we just optimize some sort of cost function to find the best calendar layout. But what we also do is prediction. So in the future, let's say that so this is your calendar schedule, let's just say Monday, Tuesday, you have to do assignment 1 and assignment 2, something like this. Right? Just pretend assignment 3. Let's say that suddenly you have work over here. So now, your time required to do assignment 1 has actually been chopped. right? And assignment 2 has actually been reduced. So what we do is we use this new data and we predict in the future what your timetable will look like in the future. Okay, so in day 2, which is Tuesday, these assignments will actually change. Because you wasted so much time on work, our algorithm will actually tell you have to spend more time on assignment, you have to spend more time on assignment 1, for example, according to the constraints, right? Everyone has to sleep and stuff. But what we can do is in the future, not just Tuesday, we can predict Wednesday, Thursday, all the way until the last day of the year. We can predict how your calendar will look like using AI. So that's what Plannero, that's the other feature of Plannero. And the other most interesting feature of Plannero is, so what Plannero does, what it can do is that we can optimize your calendar effectively using AI. You don't have to check all the combinations using old algorithms. So that's the first step, right? Finding the best efficient timetable. The second most important characteristics of Plannero is future planning. You can actually see in the future what happens to your calendar if you do something wrong. Right? So this is actually looking into the future. So this is the prediction part. And the third part that we can do is team scheduling. So this is going to be a future feature, but what we can do in team scheduling is that let's say that we have some sort of calendar, 2 calendars or 3 calendars or something. Calendar 1, calendar 2, and calendar 3 or something. Right? After we do this step and this step, now we can actually schedule correct team meetings with buffer zones and everything, right? So you won't double book, and what happens is, let's say that we have, someone has to do assignment 3, assignment 2, or project 1, right? In the real world we have projects, right? And set deadlines, due dates and stuff, also meetings and stuff. You can put anything you like into the calendar. Let's say that this person has all of this stuff, customer 2 only has assignment 1, and customer 3 has nothing. But as you can see, customer 1 has a lot of stuff. And what we can do is, using these 3 calendars, we can effectively recommend you which times is good for team meetings, right? Because we have to consider the stress of this person, right? This person has a lot of stuff on. You can't just randomly put like a meeting halfway through like a class or something, or like assignment 2 and then assignment 2 meeting. You can't do that, right? So what we can do is, with AI and optimization methods, we can recommend you the best time for all these 3 people, or n people, right? Any single number of people. We can find the best team meeting. And because of the future planning, what you can do now is that we connected both of them with team scheduling. And what you can do is, if you, for example, if you can't go to a team meeting, then we use the future planning algorithm. And we can project into the future what happens to your team meetings. Should you do it tomorrow? Should you do it the next day? And so on. Do you want to?
Okay. Thank you, Daniel. So today we are from Plannero, and this is the first automatic time management app that we have created, and Daniel has been our AI engineer. So because to start to talk about why we built this product, because 2 years back when I came from India to Australia, being an international student, and when we were doing a lot of activities like clubs, volunteers, you have so many tasks in your hand.
Stand at the front.
Oh, that's fine. Yeah. Anywhere I can speak. Okay, I will start here. I don't need to record. So basically, 2 years back when I came from India to Australia, I was studying masters in marketing, and during that time I used to be involved with a lot of activities. Like I'm sure you guys do this society, those society. I used to be involved with like 5 societies, like marketing society and this thing. And also I had my part-time internships. But the problem with I faced is, like sometimes when your manager from your internship or your office call you for a certain shift. And during that time, it's very hard for you to manage your schedule. Now, I used to use Google Calendar. How do you use Google Calendar generally to manage your tasks? Do you guys use Google Calendar? So what do you think is the problem of Google Calendar? According to you, like you face.
It can't predict things, is what you're trying to do, right?
Exactly.
Yeah.
So the problem with Google Calendar is, as I mentioned, like what if my manager called me suddenly, and what if I get sick? So I have to again reschedule my whole things, and everything is in manual. So this is a huge problem, like this reduces our productivity. So I thought, like, because I'm a very high procrastinator person, I used to procrastinate a lot. So I was like, okay, let's do something, because I came from electrical engineering background, and here at UNSW I did marketing, and then at Stanford I did design. So I was thinking how we can solve this problem. So during that time, we went to an accelerator and we created the first automatic time management app that Daniel was mentioning that will help you to allocate the right task at the best times of your day. We have a feature that he was mentioning about fast forward. For example, if your manager or you get suddenly sick, we can show you what the future will look like. That will actually improve your productivity, which actually reduces your procrastination. So we built this app, we pitched it to Accenture Liquid Studio, and Accenture Liquid Studio has been helping us to make it into a scalable product. And we recently partnered with Microsoft and Alibaba to make it into a larger base. So Daniel is our co-founder and also our AI engineer, and we are launching the app at the end of this month for pilot version. So our main goal is to get to understand what students feel about the feedback. So today we came and Daniel talked about one of these Plannero because we want you guys, it's kind of free, to use it and give us feedback how it's actually creating value out of it. Because if it is not creating value, then we have to keep iterating. So the latest version is releasing on 30th of May. So if you guys use it and tell us what's the feedback, then we can make it. Because our main goal at the end of the day, also make it into business version. So that, because procrastination is not just problem for students, it's problem for everyone. For business, the CEOs scratch their heads. Half of the CEOs don't have hair, if you see, because they're scratching their heads all the time. It's so busy time. We work at Fish Burner, so it's a huge problem. So we believe that using our app, which is the automatic time scheduling app, we can help a lot of CEOs, a lot of managers, and also students to make their life a better individual. So I would urge you guys to use this app. Danny will let you know. And if you guys, also we are hiring for an intern, so because Accenture has been helping us, Liquid Studio, and if you guys are interested, mostly AI and machine learning engineers. So if you guys are interested, let us know and we'll be happy to have you guys. Any more questions, just ask me and happy to answer.
Get the app?
30th of May.
On App Store?
App Store, App Store.
You got a website?
We also have website plus app, Google App Store, like we